Real numbers. In our previous class, we started our exploration of real numbers and encountered irrational numbers. We continue our discussion on real numbers in this chapter. Real numbers are just numbers like 1, 12.38 minus 0.8625, 3 upon 4, under root 2, 1998. In fact, nearly any number you can think of is a real number. Real number includes whole numbers like 1, 2, 3, 4, etc. Rational numbers like 3 upon 4, 0.125, 0.33, etc. Irrational numbers like pi, under root 3, etc. Real numbers can also be positive, negative, or zero. Divisibility. Definition of divisibility. A non-zero integer a is said to divide an integer b if there exists an integer c such that b is equal to ac. The integer b is called the dividend, integer a is known as the divisor, and integer c is known as the quotient. Let us take some examples to understand it better. If 15 balls are counted in 7, one will remain. Similarly, if 12 balls are counted in 5, two will remain. If 17 balls are counted in 3, two will remain. That is Euclid's division lemma, where lemma means proven statement. Theorem. If a and b are positive integers such that a is equal to eq plus r, where r is greater than equal to 0 and less than equal to b. Note that q and r can be 0 in this theorem. Euclid's division algorithm. Euclid's division algorithm is to obtain the HCF of two positive integers, say c and d, with c greater than d. It follows the steps below. Step 1. Apply Euclid's division lemma to c and d. So, we find whole numbers q and r such that c is equal to dq plus r, where r is greater than equal to 0 and less than d. Step 2. If r is equal to 0, d is the HCF of c and d. If r is not equal to 0, apply the division lemma at d and r. Step 3. Continue the process until the remainder is 0. The divisor at this stage will be required HCF. This algorithm works because HCF of CD is equal to HCF of DR. Let us explain Euclid's division algorithm with the help of an example. Use Euclid's algorithm to find the HCF of 4052 and 12576. Solution. Step 1. Since 12,576 is greater than 4,052, we apply the division lemma at 12,576 and 4,052 to get 12,576 is equal to 4,052 multiplied by 3 plus 420. Step 2. Since the remainder 420 is not equal to 0, we apply the division lemma at 4,052 and 420 to get 4,052 is equal to 420 multiplied by 9 plus 272. Step 3. We consider the new divisor 420 and new remainder 272 and apply the division lemma to get 420 is equal to 272 multiplied by 1 plus 148. We consider the new divisor 272 and new remainder 148 and apply the division lemma to get 272 is equal to 148 multiplied by 1 plus 124. We consider the new divisor 148 and new remainder 124 and apply the division lemma, and we get 148 is equal to 124 multiplied by 1 plus 24. We consider new divisor 124 and new remainder 24 and apply division lemma to get 124 is equal to 24 multiplied by 5 plus 4. We consider new divisor 24 and new remainder 4 and apply the division lemma to get 24 is equal to 4 multiplied by 6 plus 0. The remainder has now become 0, so our procedure stops. Since the divisor at this stage is 4, the SCF of 12,576 and 4,052 is 4. Notice that 4 is the SCF of 24 and 4, 124 and 24, 148 and 124, and so on till 12,576 and 4,052. Euclid's division algorithm is not only used for calculating the SCF of very large numbers, but also because it is the one of the earliest example of an algorithm that a computer had been programmed to carry out. The fundamental theorem of arithmetic. We have learned that every positive integer other than 1 is either prime or composite. If a given positive integer is a composite number, it can be written as the product of two of its factors. These factors in turn are also either prime or composite. If composite, the factors can be split up further. If we keep on doing this factorization, ultimately we will arrive at a stage when all factors are prime numbers for positive integer as shown in the figure. Theorem 1. Fundamental theorem of arithmetic. Every composite number can be expressed or factorized as the product of primes, and this factorization is unique